When your Cambridge computer science exam pushes you out of your comfort zone, you push back with perfect answers. Welcome to this Exam Strategy Explainer. Today, we are tackling the boogeyman of grades, Chapter 7, Subroutines and File Handling. Whether you are sitting for Syllabus 0417, 0478, 2210, or 9618, you cannot afford to panic when you see a massive 15-mark programming challenge. You need a system. We see so many students fail here. Let's call one of them Alex. Alex overloads his exam answers with raw computer science facts, writing massive walls of spaghetti code with zero structure, completely ignoring the analysis. Then there is Sam. Sam rushes the exam, misses the specific command word requirements, and drops crucial marks because of tiny syntax errors. Today, we are going to fix that. We are decoding the exact concepts you need to transform those messy, flawed scripts into clean, functional programs that examiners absolutely love. To really understand what Cambridge wants from you, we need to think about real-world logic. Ever played a video game that couldn't save? Imagine spending 5 hours beating a really tough boss, gathering legendary items, and finally completing a massive level. You hit exit, go to sleep, and the next day you boot it up, only to find out that closing the game deleted literally all your progress. Why did that happen? Because the memory was only temporary. While the program was actively running, your score and items were just being held in temporary variables in the RAM. But the exact second that application closed, poof, gone forever. Cambridge examiners love writing scenario questions exactly like this. If you want to build programs that actually remember data, and if you want to write code that doesn't look like a tangled mess, you absolutely need the tools we are unpacking right now. To solve these problems of lost data and chaotic code, here is our tactical blueprint for today's session. First, we are going to explore the power of subroutines. Second, we will break down the crucial differences between functions and procedures. Third, we'll master passing the parameters. Fourth, we look at permanent storage using text files. And finally, we will decode the strict file handling process. Let's jump straight in. Before we continue, subscribe to our YouTube channel, Ace the Exams, at aceexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's dive into our first major concept and see exactly how top students break massive programming problems into bite-sized, manageable pieces using subroutines. This is where we start applying our PL framework, point, evidence, explanation, link, to structure our logic. Think of programming an application exactly like cooking a massive, complex meal. You don't try to do it in one giant, chaotic step, right? Instead, you perform a series of smaller, completely independent tasks. First, you buy the ingredients. That is one isolated task. Then, you prepare those ingredients by peeling or soaking them. That's another task. You cook them at different times so everything finishes together. And finally, you prepare the table and serve. Each one of those processes is essentially a subroutine used in the main task of cooking the meal. When Cambridge asks you to design a system, they want to see you break it down just like this. Computers make extensive use of subroutines in the exact same modular way. Here is the exact dictionary perfect definition you need to lock into your brain for those standard definition exam questions. A subroutine is an independent section of code that can be called from another routine while the program is running to perform common tasks. Notice the keywords there, independent and called. It does not represent the entire system. When a subroutine is activated, which programmers refer to as being called, the main calling program is temporarily halted. Complete control is transferred over to the subroutine, it executes its specific job, and the moment it finishes, it hands control right back to the main program. Now, why does Cambridge test this so heavily? It all comes down to the advantages of modularity. If you get a question asking to state 3 advantages of using subroutines, this slide is your golden ticket. First, a subroutine can be called when needed, which avoids repeating identical code. If you need to calculate an interest rate 20 times in a program, you don't write that code 20 times. You write it once and call it 20 times. Second, it can be passed data to be used in calculations. Third, and this is the one examiners love, there's only one section to debug. Errors are completely isolated. If you have a bug, you just fix the subroutine instead of hunting through thousands of lines of spaghetti code. And finally, there's only one section to update. If you improve the subroutine, that upgrade applies everywhere automatically. So now that we understand why subroutines are the ultimate way to structure your code, let's step into the arena and compare the 2 main types you will encounter in your exam, functions and procedures. This is exactly where our student Sam always drops marks by rushing and mixing them up. Let's fix that. Pay close attention here, because this is the absolute essential difference you must memorize. A function guarantees exactly one returned value, and it returns that value directly through its own identifier, meaning its name. On the other hand, a procedure might return absolutely nothing at all, or it could return multiple values, but it does so through its outgoing parameters, not through its name. If a Cambridge question explicitly asks you to return a single calculated value back to a main program, you must use a function. No exceptions. Let's look at this comparison table to really visualize the syntax. Notice how both subroutines have very similar starts and ends. You've got function and end function, or procedure and end procedure. But look closely at the returning values row. The function relies heavily on the return keyword. For example, return num1 times num2. The procedure, however, uses an outgoing parameter, often defined with the word output, to hand data back. And look at the declaration at the top. A function explicitly states the data type it will return, like returns real or returns integer. A procedure declaration does not have that because it doesn't return a value through its identifier. Okay, so we have our subroutines, but to make them actually do the heavy lifting, the complex math, the string manipulation, the data sorting, we have to feed them data. We do this using parameters. A parameter is simply information about the data that the function or procedure is going to be processing. But here is the secret. How we hand that data over changes absolutely everything. Let's look at the first method. When you pass data by value, which is indicated in code by the keyword byval, you are essentially handing the subroutine a photocopy of your data. The subroutine holds a completely local copy. It can draw all over that copy, it can do crazy math with it, but any changes it makes are totally discarded the second the procedure exits. Your original variable sitting safely back in the main code remains perfectly untouched and altered. In fact, if byval or byref is totally omitted in Visual Basic Code, the default behavior is to just pass the parameter byValue. Passing by reference, however, uses the keyword byref, and it is a completely different beast. This method gives the subroutine the actual memory address of your data. It is not a photocopy, it is the original master document. This means any modifications the subroutine makes to that data are permanently stored directly in that original variable. When the procedure exits, the main program will see the updated, changed value. If you are writing a procedure in your exam and you need it to output a calculated value back to the main program, including byref is absolutely vital. If you forget it, your calculation basically dies inside the procedure. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCS, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at Ace the Exams IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get into our interactive workshop. Modular code using functions and procedures is fantastic for organizing logic while the program is actually running. But what happens when the user hits the exit button? Let's talk about permanent storage. Let's kick off challenge 1, the data scan. I'm going to put 60 seconds on the clock in a moment. I want you to extract the core trend from this examiner logic. The source text states, once the system is exited, the data will be lost. The next time the program is run, the variables will hold the initialization value that had been coded. This means all those high scores, player names, and complex calculations literally vanish into thin air. Time's up. The core trend here is that RAM is volatile. This makes external file handling an absolutely vital skill for any real-world application and a guaranteed high-mark question on your paper. We have to take the data from the temporary variables and write it to the physical hard drive. The most fundamental way we achieve this permanent storage in the Cambridge syllabus is through a basic text file. A text file is a simple, highly accessible form of permanent data storage. It stores data as plain text and is normally saved with the .txt extension. Whether you are using Visual Basic StreamWriter class in a practical exam or just writing pure pseudocode on paper, text files are your universal starting point for saving a program state. Now, saving data to a file is never just a single magical command. It is a strict, rigid, sequential process. If you skip even one step here, your program fails, the data corrupts, and the examiner crosses out your answer with a red pen. Welcome to Challenge 2, Find the Flaw. I want you to listen closely and figure out where students lose the most marks. You must always follow this 3-step universal golden rule for file handling. Step 1, open the file. But you can't just casually open it. You must explicitly specify the mode of operation. Are you opening it for reading or for writing? Step 2, perform your read or write action using the correct variable. And step 3, did you spot the flaw students make? It's right here. Step 3 is close the file. Sam forgets this constantly. If you omit the close step, the file remains locked in the system memory. The write process won't actually be completed, and when the program exits, nothing saves. Always close write you open. Time for challenge 3, speed writing. You've got 30 seconds to visualize writing the perfect PEL paragraph based on this pseudocode. Look at the syntax. First, open file score.txt for write. You state the file name and, crucially, the for write mode. Then, write file score.txt, high score. You state the file again and then the variable holding the data you want to permanently save. Finally, close file score.txt. In a language like Visual Basic, you'd use a class library like system.io/streamwriter, declaring an object instance with as new, passing the file path. But the logic, open, write, close, remains absolutely identical. Now, what about reading that data back when the game restarts? The reading process is almost an exact mirror image. You start with open file score.txt for read. The only difference is the mode of operation. Then, instead of writing out, you pull the text back into your program's variables using read file score.txt, start high score. And once again, you finish with close file score.txt. Writing or reading, it does not matter. You must follow the sequence. But wait. Let's inject some advanced, real-world logic here to secure those final few A-star marks. What happens if your program tries to open a save file to read the high score, but the user accidentally deleted it from their hard drive yesterday? Or what if it's the very first time they have ever launched the application? If you just blind fire a read command, the program will crash violently with an error message, usually a file not found exception. Your code stops dead in its tracks. This is why top-tier developers and top-scoring students always use an existence check. In Visual Basic, you'd use the system.io.file.exists function wrapped inside an if statement. You check if the file exists first. If it returns false, you gracefully output a message like file not found, or you create a new one. If it returns true, then and only then do you proceed to open and read it. This error-catching logic is the hallmark of a truly robust program. We've built the ultimate computer science answering system today. Remember the 3 rules that guarantee top marks. First, command word decoding. Know exactly what the question is asking. Second, apply the PEL framework to structure your code explanations. And third, use a time management matrix so you don't rush like Sam. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing right now. Our team responds to every single comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.